Welcome back to our session. We're still looking into the role of energy in as far as a chemical change or a reaction is concerned. By now we appreciate the fact that in as far as bond energy is concerned, we require a certain amount of energy to break existing bonds within, the reacting particles. And while the process of, formation of new bonds or new products happens, energy is actually released. So by now, we are familiar with the concept of bond energy, okay, which gives us an indication of the amount of energy required to break a bond, which is the same for the same type of bond, which is released when that new bond is formed. So for now, we'll focus our attention on energy profiles, based on the fact that we want to make a comparison between the total amount of energy absorbed when bonds are broken versus the total amount of energy when bonds are broken. So we'll look at the two types of reactions, which is, your exothermic and your endothermic, right? Okay, so the law of conservation of energy is very clear in terms of, what happens in a closed system, okay? So we know that energy cannot be created or destroyed, but energy can be transformed from one form to another. So in a chemical change, when we break bonds, we don't, destroy energy. While equally, so when we form new bonds, energy is released, but we are not creating new energy. We're just transferring energy, or transforming rather, energy from one form to another. So there are two broad categories of types of reaction. We've got an endothermic reaction in which the net energy is actually, absorbed. More energy is absorbed. So energy is not destroyed when bonds are broken, in a chemical reaction. And also in an exothermic energy reaction, which actually releases energy, we actually do not create energy, but the key term or keyword is energy conversion or energy transformation. Right. So the two broad categories of reaction or types of reaction is endothermic, in which here we are saying that more energy is absorbed, right? Is absorbed than released. Okay. So what we're simply trying to say here is that in an endothermic reaction, there is both absorption and release of energy, but in an endothermic reaction, more will actually be absorbed in comparison to what is released when new bonds are formed. And then when we talk about an exothermic reaction, we are saying that more energy is actually released, okay, than absorbed, okay? So in other words, we are trying to drive the point that in these two types of reaction, there is both the release and absorption. Then it will entirely depend how much we absorbed versus how much is released when new bonds are formed. So if we can look at the energy profiles, which actually show the changes in energy, okay, from when we start with the reactants and we form new substances, which are actually the products. Okay, so all substances, they possess energy according to the kinetic molecular theory. So this is a very, very important point to say that any substance in its very existence, it contains some form of energy. Okay, whatever state it is, it can be a solid, it can be a liquid or a gas. And at the very lowest amount or quantity of energy with the solids, the vibration of these particles of a sample of a solid substance actually suggests that any form of matter does contain some energy. Okay, but then what will then differ is the amount of energy that we require to actually, break those existing bonds, right? So all substances, according to the kinetic molecular theory, they actually have or possess some form of energy, okay? So then we've got, while talking about energy, for any reaction, we know that energy is absorbed to break bonds, ne? Energy is absorbed, okay, for bond breaking, all right? Right. So to break bonds based on, and the amount of energy will entirely depend on the bond energy involved. Okay. So, and then also energy is released. Okay. During bond formation. All right. So this is a very, very important point that we need to always make reference to. Okay, so but then for a reaction to start, there's a certain minimum amount of energy that is required for a reaction to take place, and that minimum amount of energy is called the activation energy. So the symbol E subscript capital letter A suggests that it's for, you know, an activation energy. So if, say, for argument's sake, a particular chemical change or reaction requires, let's say, 50 kilojoules of energy for it to start. Okay, so if we supply that reaction with 40 kilojoules, it certainly means that the reaction will not take place. Why? Because the minimum or the threshold that is actually required is not sufficient based on what is supplied. So anything beyond or equal to or greater than 50 kilojoules of energy will actually start that reaction. So that's the emphasis is on the minimum, which is actually the threshold, right? So the SI unit of activation energy is kilojoules per mole, right? So if you look at the energy profile for an endothermic reaction, you'd realize that the reactants which are, are at a particular energy level. So this is the energy level of the reactants. So we have agreed that according to the kinetic molecular theory, all substances possess some form of energy. So for this reaction to take place, we actually need to supply energy to break bonds, okay? So if you think of it, this is the minimum energy that is required for this reaction to take place. So that's the amount of energy that is absorbed. So this is what is absorbed, okay, the minimum. It can be this or more for this reaction to take place. So once these reactants absorb energy, when they reach to a certain stage where now they are able to start forming, the products or the new substance, we have got what is called an activated complex. So this is an intermediate stage between reactants and products. At that time, we are saying that the existing bonds are quickly being broken, and at the same time we are starting to form new substances. And as we form new substances, the energy in that system actually starts to decrease. Why? Because as we form new substances or new bonds, energy is released. That's why there is a drop in energy. Okay, so the absorption in this case is coupled to energy from the surroundings, being supplied to the reaction. That's why there is an increase in the energy of the system. Okay, so while the new bonds are being formed, there is a drop in energy, all right? So the minimum that is required for this reaction to take place is our activation energy. That's our activation energy. So this interval of energy represents the minimum, okay? So this is what is absorbed, okay, in terms of energy, and then this is what is released, okay? Then we are able to say in an endothermic reaction, more energy is absorbed than what is released, okay? Right, and then that's the, the profile. And then when it comes to the activated complex, we are talking about that unstable intermediate state between the reactants and the products. So what is actually happening when we reach that stage, which we refer to as the activated complex? We are in, halfway in between, the two processes of bond breaking and bond formation are beginning to occur. So we are having these reactants, they are, the existing bonds are being broken, while at the same time, we have got new bonds being formed. And remember, when we break bonds, energy is absorbed. So we may supply energy from external energy, in the form of heat to break the bonds. Then when immediately we start forming new substances, the energy is released. That's why the profile shows a drop in energy. And then that's why we say at the end of the day, when new bonds are formed, energy is actually released to the environment, right? So the activated complex is that intermediate state between reactants and the product. And we get to understand the role of energy in as far as, a chemical change is concerned. So if we talk about, for argument's sake, in the reaction between hydrogen molecules and oxygen molecules to form water molecules. Okay, so between at that activated complex state, we have got a scenario like this where we are starting to form new bonds while the old bonds have been broken. So we are almost there in terms of forming the product. So this is how you'd want to think of, you know, the activated complex. So it's that intermediate state, right? Okay, so in as far as this endothermic reaction, we are saying that the amount of energy absorbed, let's say for argument's sake, this is 50 kilojoules per mole, okay? And then that's, let's say 90 kilojoules. Now, the amount of energy absorbed is the interval between 50 and 90, which is actually the minimum, which is our activation energy. So our activation energy in this case is actually equals to 40 kilojoules per mole, right? That's the minimum, okay? And then we are saying that these reactants are at an energy level of 50 kilojoules per mole, while the activated complex is 90. So the difference in that gives us the activation energy. And then we know that 40 was absorbed. Amount of energy absorbed, okay? So the energy absorbed in this case is equals to, we know it's 40 kilojoules per mole as an example. All right, and then how much is released? From 90, let's say this is 60 kilojoules for argument's sake. So the products are at that energy level. So energy released, right, is equals to, we have released from 90 to 60, we have released 30 kilojoules per mole. So what are we saying here? We are saying that more energy is absorbed than released. Hence, we would refer to this as an endothermic reaction. So at the same time, we are saying that the products are at a higher energy level than the reactants. That's why we are saying more was absorbed than released. Right. So in an endothermic reaction, in a nutshell, at the start of the reaction, energy is absorbed like in any other reaction, and the energy of the system increases. And then bond breaking, which takes place as a result, results in the new bonds being formed. And while we form new bonds, energy is released, okay? So the release of energy is coupled by formation of new bonds to the surroundings. That's why there is a decrease in the energy of the system. Okay, now we're just trying to explain the profile. So in an endothermic reaction, more energy is released than absorbed. This is what we take home. Now, at the end of the day, we're saying that the enthalpy change is positive when more is absorbed than released, right? So that's as far as the endothermic reaction is concerned, that in terms of energy, there is more energy by comparison that is absorbed than what is released. So for now, we'll take a short breather. When we come back, we'll take more discussions on, you know, the other type of reactions in as far as energy is concerned. Let's take a short break for now.